So hopefully the screen is visible, the writing screen.
Yes, sir.
Okay. In the previous class, we were talking about the Bernoulli's equation, and we came up with certain restrictive conditions under which the same could be applied. So I will start with the restrictions one by one. So the first restriction, so we'll start with the restrictions one by one. The first restriction is inviscid flow. This is with which we started, and there is no compromise with this. The second assumption that we made in the way, I'm just putting up the points in the order in which we used them for simplifying the equations. The second one we put is the gravity as the only body force, and that also acts along the negative z direction. So these two were the preliminary ones that led to the following equation. So these two led to this. Now from here, we made a couple of more simplifications. Steady flow, so that the first term is not there. Constant density. And G is not a function of Z. And that led to the simplified form. Then we made some further considerations. Now the further considerations are the following. Irrotational flow. So the further considerations were with a motivation of finding out the conditions under which this term is zero. So one is irrotational flow, which is equivalent to the vorticity as a null vector, or dl along a streamline, or maybe just another possibility. This one. So when that is also satisfied, we come up with this one, d of p by rho plus v square by 2 plus gz is equal to 0, or p by rho plus v square by 2 plus gz is equal to constant. So from here, what can we conclude? This is one of the very common questions, and perhaps a very favorite question in some of the interviews or other formats of exam at different levels. That what are the assumptions that lead to Bernoulli's equation? Well, the assumptions are quite a few, and it is better that we systematize it and refer to them in the context in which they appeared for deriving it. So the inviscid flow and gravity as the body force along z direction, negative z direction, steady flow. I mean, for the steady flow, I want to give you a rider that there is something called as unsteady Bernoulli's equation, which we will discuss subsequently. So when we talk about Bernoulli's equation, normally we talk about the steady version of the Bernoulli's equation, and that is why steady flow. But there is also unsteady version, and that is quite clear because in the unsteady version we'll simply retain the unsteady term. Constant density is something which is a way to convert dp by rho as d of p by rho. Now I asked you one of the key questions, that other than constant density, do you have other possibilities for which you can write dp by rho as equal to d of p by rho? Any one of you want to give an explanation to this? So the first answer that I am giving you, which is a very clear answer, that other than constant density, which is the trivial case, there are other cases, or there could be other cases for which you can still write d of p by rho as equivalent to dp by rho. So can you tell maybe one or two such examples? Any one of you, and you have to justify why. One of you. So nobody want to tell anything about this? So I will get this answer only from you. I mean, and so long as I do not get a response, I will hold the discussion on this topic for a subsequent day. The topic of this dp by rho, to an extent that some of you at least will give some thoughts, and then I will of course tell a bit more insight. So for the time being, we are considering constant density, but with a rider that it could be a bit less restrictive than constant density. Although, I mean, if we say constant density, it safeguards everything. Now, I know that if you refer to books, it will write incompressible, not this term constant density. Often, with years of teaching experience, I, sometimes I am a bit cautious and sometimes over cautious in putting up the correct terminology. And here, very purposefully, I have not used the terminology incompressible here. Instead, used constant density, which you may relate very easily, from the derivative operations. That is, if something is a constant, you can put it inside the derivative without a problem, and that is what you want in this term, nothing more than that. But the obvious question comes that when in the books it is written that for Bernoulli's equation the flow has to be incompressible, does it mean that this is wrong, or is there a correlation between this? So of course, constant density will imply incompressible, but incompressible will not always imply constant density, as we have discussed earlier. But the bigger question is, if it is a variable density incompressible flow, that is incompressible but density is variable, can we still use this equivalence? So see, the depth of thought that you have to give for it. It's not just a casual statement of incompressible flow that we may need to consider. So this is also a corollary question to the previous question that I have posed. For the time being, you can take density as density equal to constant is a sure shot assumption, and G is not a function of Z, so that you can take G inside the derivative. This is something which is normally going to work, except for large scale atmospheric flows, where if you go to the outer atmosphere, the acceleration due to gravity will change and it will not be the same as it is there on the Earth's surface or close to the Earth's surface. So these are the assumptions which many of which are a bit subtle but more obvious. What is normally not so obvious is the sequence of assumptions or the different possibilities concerning this term. So now to understand the implications, let us look into this, this so-called Bernoulli's equation, where we say P by rho plus V square by 2 plus GZ equal to constant. Now the question is it a universal constant? Universal constant means not universal in a sense that for all problems, that is at all points in the flow field or flow domain, the constant is same. So P by rho plus V square by 2 plus GZ equal to C. My question is the value of C same at all points in the flow field? Can any one of you answer to this?
So it is constant along one streamline, right?
You look at the last thing that I have written, this one. I mean, take away all the prejudice from your mind, what you have learned earlier. Just erase it. I mean, imagine that there is an eraser and you are erasing what is there as a prior education that you have learned. Just look into this and give an answer. And if you can do that, I'm sure you will give the correct answer. Any one of you.
Hello, sir. If the flow is incompressible and variable density, then this equation may not be true.
No. I mean, I'm not coming into that, incompressible variable density, etc. That discussion I told that I will hold, unless some of you, think and give a very sort of concrete thought about that. I'm talking about that, given that, all these things are passed, and we are coming into, so constant density. So I'm not talking about incompressible. So constant density means, this has passed. See, this has nothing to do with, I'm talking about, this is equal to constant, and this has nothing to do with, constant density, because the constant density is already taken care of by this one, P by rho. I'm talking about C, and from here you will get an idea that C is not actually dependent on the density related matter that we were talking about. It is dependent on something else. So as I can repeat my first question, that is C a constant value for all points in the flow domain or flow field where the fluid flow is taking place. Yeah, I mean, any one of you give.
Sir, if it is an irrotational flow, then it will be constant at any point. But if it is a rotational flow, then it will be constant only along a streamline.
Yes, almost correct, but something a bit more has to be added. So, if you see irrotational flow will set this term to 0 irrespective of any other condition. That means that if we have irrotational flow, this term will be 0. No other condition is required. So that means D of that is equal to 0 without any restriction except irrotational flow restriction. That means this is equal to constant, and that constant does not have any other restriction. So what the first observation means that if the flow is irrotational, then this constant is a constant that is having the same value at all points in the flow domain. But here there are odds, right? I mean, if this is not satisfied, there are other conditions also for which you can apply the equation. The second condition, dl along a streamline. So if you consider dl along a streamline, that restriction should be there somewhere implicitly. That means that this constant will be a constant only, will be a particular value only along us, with reference to a streamline. That means that you can apply this equation, that is P by rho plus V square by 2 plus GZ equal to constant, a particular constant only along a particular streamline. Along a different streamline, the constant will be different. So in other words, if you write, if you have a streamline, so if you have P by rho plus V square by 2 plus GZ equal to constant, that means P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. So this means that we are having the 1 and 2 points on the same streamline. For irrotational flow, that restriction was not there. So the 1 and 2 points could be any point 1. So if this is the flow domain, any point 1 and any point 2, no matter whether they are located on the same streamline or not. But if it is not irrotational flow, that is a restriction. But then up to this is if you are very, very careful and you have learned your previous lessons well, even without going through these derivations, this much of knowledge you are likely to have. But if I say that even if it is not irrotational flow, even if we are not considering a specific streamline, still we can use this. Yes, there is a third possibility here, that your choice of dl is such that your velocity cross vorticity is having a direction which is perpendicular to dl, and then instead of streamline, along the direction of the dl, if you take any line, you can apply this equation. So that will be constant along that line. So I hope you can follow this. That the third or it gives the possibility of using this equation along a line or a direction which is not a streamline, but the direction will fulfill this requirement, that is V cross omega perpendicular to that direction. So if that holds, then this constant will be a constant along that line. So if you choose a different line for which this is valid, then along that different line there will be a different constant. So what it means, that at the end, Bernoulli's equation is quite restrictive, and restrictive in a sense that a large number of assumptions are compulsively required to put this equation into validity. So with this, now let us look into a bit of the physical aspect of the Bernoulli's equation, that what it actually talks about. So if we say that at the end this is what it is. This is the Bernoulli's equation. So it tells that sum total of three things is a constant, either a constant over the entire flow field, or a constant along a streamline, or constant along another specific line. Whatever it is a constant. So what does it actually mean? So to give it an interpretation, we will start with the terms which are intuitively more obvious to describe or to explain. So V square by 2, you can say half mv square by m, right? I'm just again see every time I try to give some interpretation, I try to adhere to a school level exercise with a clear understanding that this is perhaps not the most rigorous way to do it, but it can connect us with our prior knowledge, whatever we have learned, and that is how we synthesize it better. So half mv square is the kinetic energy, and that divided by mass, you can say this is at least dimensionally kinetic energy per unit mass. Similarly, Gz, you can write mgz by m. So mgh is the, so z is like h, height. So this is potential energy per unit mass. So you have kinetic energy per unit mass, potential energy per unit mass. So then the question is, what is this? I mean, is this in schools? It is sometimes called as pressure energy. Again, maybe per unit mass, because other terms are per unit mass. But the only trouble that I have with this is not that I am not ready to accept pressure energy as a term, but what I am saying is that kinetic energy and potential energy give us an intuitive feeling of their physical meaning. So kinetic energy is the energy which is attributed to the motion of the either particle or body or whatever, and potential energy is configuration. So in this case, it is a gravitational potential energy. You could also have potential energy due to stretching of spring like that. So it is due to configuration. Now that much we understand, but pressure energy is something which is just from the term. I do not know. I mean, some people may have great idea and they can understand it obviously, but I am not able to understand it obviously. What is meant by pressure energy? except that I know that this may be a good term in the book to remember and reproduce. So therefore, let us get a little bit deeper into what it could be. So let us take an example of say a pipe in which there is some fluid, or rather initially there is no fluid, but the fluid is being continuously pushed by a pressure gradient. So you apply a pressure differential and fluid is entering. So let us say that by this pressure differential, and this is a continuous pressure differential, fluid is being pushed by a distance delta x. So this is the pushing of the fluid, and why just a small distance delta x I have considered is because the pressure is likely to vary continuously along the x direction. So I have taken a small delta x over which pressure is roughly not changing much. Let us say that A is the cross-sectional area of the pipe, and for circular pipe it is pi r square, but it could be something other cross-section also. So now you see this pressure differential is actually applying a force so that this so-called fluid element is being pushed and the work is done. So what is that work done? In pushing this fluid element, so this is equal to so if you have the pressure as P here, so it is P into delta x. So delta P is manifested by say a pressure P here and pressure 0 here. So when you have a pressure P here and a pressure 0 here, so it is actually applying a pressure differential delta P. So let us say that locally the pressure is P. So when you have the local pressure P, the work done is just remember the thermodynamic work done PdV. So P into delta x into A. Okay. So the work done, which is P into delta x into A, because the you can imagine the work is related to displacement also, which is the force times delta x, and the force is, so this is just like P into A is the force, that times delta x. This is the force into displacement. So the force which is acting on this fluid element is P into A, and that is creating a displacement of the fluid element delta x. So that this displacement is very, very important, because this is what is enabling the maintenance or sustenance of the flow. And if that is not there, the fluid will be stagnant. It cannot really move. So this is the work done. So the work done, so because these energies are expressed per unit mass, so this work done per unit mass is P delta x into A. And what is the mass of this shaded element? That is nothing but density into the volume, right? So you can see these are cancelled, and this card turns out to be P by rho, right? So you can say that whatever it is, the name, I do not care about the name, but whatever it is, this P by rho is work done per unit mass to maintain the flow as attributed to the pressure or in presence of pressure. So this is called as normally this work done can be expressed as either per unit mass or per unit weight. So for example, if you want to express this as per unit weight, what you have to do is simply divide all the terms by g. So then it will be per unit weight. So then you can divide this also per unit weight. So this physically means the work done per unit mass to maintain the flow. Normally in thermodynamics, a similar consideration. See, there is a very nice merger of thermodynamics with fluid mechanics, and that merger will be more apparent if you have a deeper understanding of the two subjects. So when we talk about this work done per unit mass, normally in thermodynamics we talk about this work done per unit mass. In fluid mechanics, we talk about this one per unit weight. Normally, I mean, this is just a way of representing. Why? Because if you normalize with per unit weight, then you will get the unit of length. See, if you normalize per unit weight, then all the terms will have a unit of length. If you divide by g, this will have z, which is unit of length. All the terms in the same equation should have the same dimension, and all have the same unit, that is the unit of length. So that is energy, whatever kinetic or potential energy per unit weight. And in fluid mechanics, this is called as head. So this is important because typically in civil engineering or piping engineering, this length unit, head has a length unit. So this has a length unit. This is often used to express the energy. So for example, typical civil engineers will say that it has a say 10 meter of kinetic energy head. So something like that. So energy per unit weight. Now this work done per unit mass to maintain the flow in presence of pressure, this in thermodynamic terminology is called as flow energy or flow work. This is in terms of terminology more authentic or correct one, not really pressure energy. Although I have no real objection if you tell it pressure energy or whatever you want, provided you understand this physically. That is more important rather than just the terminology. So this is representative of energy that is there to maintain the flow in presence of pressure. So if you see this one, this work done per unit mass, that is P by rho. If you have studied thermodynamics in an engineering course, then 1 by rho is called as specific volume. So that is terminology which is used in thermodynamics. It is absolutely nothing new. It is just inverse of density. So it is given a typical symbol of small v. So this is like small v, P into small v. So this is the the flow energy or flow work. So if you recall, in thermodynamics, if there is a thermal system, its thermal energy when the system is not flowing, that is it is not a flowing system, its thermal energy is represented by internal energy. That is a form of energy which is different from the kinetic and potential energy. and it is attributed to the motion of the molecules, the rotation, vibration, translation, etc. In a random scale, which is dependent on the temperature. So that is why internal energy is dependent on temperature, and it is also dependent on other things, like it is also dependent on pressure, except for ideal gases, where it is just a function of temperature. Otherwise, it is a function of both pressure and temperature, because this random motion will be dependent on both of these. So this internal energy, let us say it is, again I am using the thermodynamics book notation. I am confusing here a little bit to those who have not studied thermodynamics as a engineering subject, but internal energy all of you know. I am just using a symbol U, because this is mostly familiar with most of the thermodynamics books. So when the system is stagnant, we talk about the thermal energy represented by internal energy. But when the system is flowing, the thermal energy is not just this one, but in addition the flow energy or flow work, because that is what is enabling the fluid to sustain the motion. And in that way, you have to add PV, or this flow energy or flow work, with the internal energy, and this is known as enthalpy. So I am giving here you a physical perspective of why enthalpy is considered to be the correct way of expressing the thermal energy in a flowing system, whereas internal energy is the correct way of representing the thermal energy for a non-flowing system, because the difference between the flowing and a non-flowing system is attributed to this aspect of the energy. So now what we can summarily say is that whenever we have a form of energy, the form of energy is responsible for what? So is the fluid possessing this energy? That means, so let me just clear this portion. So the question is the fluid possessing this energy? So possessing this energy means that just like you have a block in mechanics, say the block is being thrown by somebody to a certain height, right? So it has a velocity, it has a kinetic energy, it is at a height, so it has a potential energy. So this is the energy that is possessed by the block. So similarly, is this the energy possessed by element of fluid? Is that we are talking about? So we are not actually talking about that. Here, it is not the energy possessed that we are talking about, but the energy transferred that we are talking about. So to give it a physical perspective, let us imagine that there is a conveyor belt. So there is a conveyor belt. Say this is a conveyor belt in an airport, where you put up a suitcase. Okay. So you put up a suitcase, and this suitcase, the conveyor belt is continuously moving. So this suitcase, by virtue of the movement of the conveyor belt, is coming here. Not that the suitcase itself is having any form of authority to do that. Just because it is being it is being pulled by the conveyor belt. So instead of this suitcase, we can imagine it as a packet of energy. So what is that packet of energy? It is kinetic energy plus potential energy plus flow energy. So what this simply says is that this packet of energy is simply transferred. It is never possessed at any point. So in that way, the sum total of the kinetic, potential and flow energy remains conserved as it is being transferred. It is conserved because we have considered that there are no dissipations. Like one obvious way of considering that there is no dissipation is the consideration of inviscid flow, because if viscous effects are not important, there would not be any explicit mechanism of dissipation. So if there is no explicit mechanism of dissipation and the only force which is acting is gravity, which is also a conservative force. That means why gravity is a conservative force, from your basic mechanics you will know that, let us say I have the point 1 and the point 2. Now I am just lifting the block from the point 1 to the point 2, either by this path or by this path or by this path, whatever. But the work done against gravity will be mgh, which is dependent on only the vertical height difference between the 2 points. It is not dependent on the path, and that is the hallmark of the conservative force gravity, and that is why you can express the corresponding energy as a potential energy. So anything which can be expressed in the form of a potential is fundamentally of conservative nature. So here we have a conservative nature because there is no dissipation, and in that way sum total of kinetic energy, potential and flow energy and flow energy transferred remains constant in the absence of any dissipation. So that is what is the physical meaning of the Bernoulli's equation. So we can perceive it as a way of describing the conservation of mechanical energy, because we have not really considered any other form of energy beyond mechanical energy. For example, we have not considered any thermal form of energy. So or electrical, magnetic, etc. And therefore, I mean, we are restrictive to only mechanical forms of energy here, and it is simply in a way reminiscent of description of the mechanical energy conservation. So this is about the Bernoulli's equation, and the next a small point that I will add to this before we stop today's class is that although we have maintained a restriction of steady flow, but the Bernoulli's equation can well be extended for unsteady flow. So extension of Bernoulli's equation to unsteady flow. So this is unsteady Bernoulli's equation. I mean, this is how this terminology is known. So this is extension. This unsteady word is important because otherwise, by default, when we talk about Bernoulli's equation, we will imagine it's the steady version. So what I will do is that I will write that equation from which the Bernoulli's equation came after retaining the this one, the unsteady term, which we dropped in the previous derivation. Right hand side we are assuming 0 because either of the three conditions which I have mentioned, let us assume that they hold. So out of the three assumptions, one assumption is that, one consideration is that DL is along a streamline. So let us take that as a specific example. Example 1, DL along a streamline. The other example like irrotational flow, we will take the example 2. First we will take DL along a streamline. So if we take DL along a streamline, so let us say this is the streamline. So streamline is a beautiful system in terms of coordinate. I could ask you a question why, but just for the interest of time, I am trying to give an answer upfront by myself. So if you look at any flow, I mean one dimensional is a very special case, but in most of the practical situations, it is at least 2 dimensional, if not 3 dimensional. So a streamline is there for all the types of flow. Doesn't matter whether it is 1 dimensional, 2 dimensional, or 3 dimensional. And once you have a streamline, the beauty of the streamline concept is that at a particular point on the streamline, see, it is a curve. So how is a curve defined? It is defined by its unit tangent, or it is better to say streamwise coordinate, which is the local tangent, and the cross streamwise coordinate, which we call as maybe the normal. Okay. So you have a streamwise and a cross streamwise coordinate. The velocity of flow is always along the streamwise coordinate of the streamline. Right? That is the definition of the streamline. We cannot really argue about that because it is defined in that way, that the velocity is tangent to the streamline. Therefore, no matter what could be the velocity field, but locally it is always aligned with the direction of the tangent, and therefore the streamline converts a 3-dimensional problem to a local 1-dimensional problem. I'm sure none of you have ever thought of the utility of streamline in this way, but this is what the reality is. In terms of problem solving, it converts an arbitrary 3-dimensional problem into a local 1-dimensional situation or unidirectional situation so far as the velocity is concerned. So in that way, you can write this DL as the unit vector in that direction into ds. So let us say that you have a small element of the streamline ds. So the length vector dl is the magnitude of this length times the unit vector. And what is the velocity? Velocity is v into this unit vector along s, because by definition of streamline v is along this one. So v dot dl, if you say, I have just put a vector here. So where this scalar v is simply the magnitude of the velocity, and arrow at the top is a vector v, which is a scalar v times the unit vector. So v dot dl, if you write, so if you take a dot product of these two, it will be simply v ds. So this will therefore become just a scalar term. So if you are integrating this equation, the left hand side of the Bernoulli's equation with all the steady terms, you can also integrate this along a streamline, maybe from point 1 to point 2. So that is the only addition of term when the Bernoulli's equation is extended to unsteady flow along a streamline. So just to summarize, that the steady version of the Bernoulli's equation may be extended to unsteady situation. In the case when we are applying it along a streamline, this is the specific term that you have to add along with the other terms when you are integrating the Bernoulli's equation between the 2 points 1 and 2 on the streamline. Let us say this is 1 and this is 2. So with this, let us stop this class, and thank you all very much. So if you have questions, you can still hang around. I'm available, but in case some of you have classes, you can just join your subsequent class. But if you have your questions, you can put up here.
Sir?
Yes, yes.
In case of Bernoulli's equation, the kinetic energy and potential energy come from the conservative force field, right?
No. I mean, potential energy comes from a conservative force field. Kinetic energy has nothing to do with conservative force field. It comes from the inertia of the fluid.
But it depends upon the endpoints. I mean, from point 1 and point 2, and doesn't depend upon the path it takes.
No. Kinetic energy. See the difference is that we are not talking about the difference in kinetic energy aspect. See, the potential energy relates to work. The kinetic energy does not directly relate to work. That means at some point, if you have the velocity, you can say what is the kinetic energy. I mean, without referring to any work. I mean, when you refer to work, you can say, in fact, in a dissipative system, you will have a drop of kinetic energy because of the work done to overcome the dissipation. Say imagine imagine a simple system. You have a friction. I mean, you have say a surface on which a block is moving with friction. So when you are talking about the kinetic energy, so let us say at one point, at the point 1, the block has velocity v1. So its kinetic energy is half m v1 square. When it goes to that point 2, its kinetic energy is less because it had to use a part of that energy to do work against friction. So half m v1 square minus half m v2 square in that simple mechanics problem will be the work done against friction. So that is the integral of the friction force times the displacement. So what I want to impress upon you here is that the concept of kinetic energy doesn't have any conservative tag with it, whereas the concept of potential energy itself has a conservative tag with it, because the concept of potential energy is actually related to the work done in certain ways. For example, gravitational potential energy is to create a displacement against the gravitational force. Similarly, the configurational is like a sort of stretching of spring, etc. is a displacement to disturb the configuration. So in that way, you will always have different physical effects. In some case, the physical effects are conservative and the description of potential energy directly relates to that. Whereas the description of kinetic energy as an expression half mv square, that doesn't depend on whether you are there in a conservative force field or a dissipative force field.
And same with the case of flow energy, right?
Yes,
I mean,
yes.
irrespective of
Flow energy also, it doesn't matter whether you are there in a conservative flow field or in a dissipative.
we just study the flow. velocity flow field. That's it. I mean, we
in fact,
doesn't
all this, see, even the potential energy in a non-conservative field, in a field where other non-conservative forces are there, still we call it potential energy. We do not call it anything else because the energy component, which is the potential energy, is attributed to a conservative force. That doesn't mean that there will not be any other non-conservative force in the entire system acting. So simply in a dissipative system, sum total of these three will not be conserved. But in a dissipative system, these things will all be there.
Yes, sir. I mean, irrespective of the process followed, those will remain constant. Like isothermal process or isobaric process, whatever.
No, I mean, see what we have discussed today is not dependent on any process. We have simply told that it's a conservative system. That means there is no dissipation. So if there is no dissipation, that is a much more general statement than what is the specific process that the system is undergoing.
Okay, sir.
Any other question? If not, so let us stop the class today and we will continue on Monday.